Okay, so this is the third part. I want to do applications now of difference equations. So, who here has seen Star Trek 4? The Voyage Home. Oh, he's not here. Okay. So the premise is an alien race is very upset that the whales have become extinct and is going to punish humanity by destroying us all. So in order to prevent this from happening, the crew of the Enterprise on a stolen Klingon ship travel back in time to bring forward two whales. Okay? And they're named George and Gracie. And so the question is, population dynamics. Imagine I have a population and I want to understand how the population evolves over time. So what we'll do is we will assume a very simplified world where humanity was almost destroyed because we caused the whales to go extinct. So we will make sure that the whales are protected. No one is allowed to prey on the whales. They will die of old age and there will be no predators. This is an absurd assumption. But this is the first order model. So the first order model is there are no predators. Let's just understand what happens. Let's simplify things. Let's say whales, whenever I talk about a whale, I will always assume a pair of whales, a male and a female. And whenever I talk about them giving birth, I'll always assume they give birth to a pair of whales. You could, of course, modify this, and you could talk about whales giving birth to just one or two or three or four, and then talk about the distribution of sexes. Let's just keep things as simple as possible. So let's say whales die after 4 years. They have two pairs of whales at 1 year, have one pair at 2 years, and then no more reproduction. So this is, of course, again, another unreasonable assumption. But if you have a large population, you might say, well, this fraction of people in this range will give birth to this many people. And we want to try to understand how this evolves over time. How many people are comfortable with matrices? So we can look at the Fibonacci numbers through matrices. So we'll put this on hold for now, and we'll look at Fibonacci's by matrices. So I'm going to let my vector Vn be Fn minus 1. So Vn plus 1 would be Fn plus 1 Fn. And it turns out I can create a transition matrix that will transition from vector Vn to vector Vn plus 1. Why? Well, Fn plus 1 Fn, well, by the Fibonacci relation, Fn plus 1 is just Fn plus Fn minus 1. And so if I want to write this, I can write this as 1 times Fn plus 1 times Fn minus 1. And then down below I have 1 times Fn plus 0 times Fn minus 1. So this goes back to the common theme of trying to understand algebra. Just making sure the cover is on. Excellent. So if I want to write this in matrix form, this is the same as the matrix 1, 1, 1, 0, acting on Fn minus 1. So now when I do the multiplication, I'll get Fn, 1 times Fn plus 1 times Fn minus 1, 1 times Fn, 0 times Fn minus 1. So the vector Fn plus 1 Fn is, let's call this matrix A, Fn minus 1. So A transforms me from one state to the next. Well, if I wanted to transform two states, what would I do? Do it twice. And so this is very similar to what we did before, the lather, rinse, repeat. So we have Fn plus 1 Fn is A, let's do Fn minus 1, or A times Fn minus 1, Fn minus 2, or A times times Fn minus 2, Fn minus 3. And you go all the way down to F1, F0. And the hardest part is always remembering how many A's do I have to get down here. And the way I always figure this out is, well, let's see. I have an Fn minus 1. I have 1 power of A. 1 plus n minus 1 is n. I have 2 A's. I have an n minus 2. 2 plus n minus 2 is n. So if I have 0 here, I have to have n over here. So I get Fn plus 1 times Fn is A to the n times F1, F0. So once I know the initial conditions, all I have to do is take a high power of this matrix A. Now, the question is, how easy is it to take a high power of a matrix? So if people are interested, this was one of the greatest advances in 20th century mathematics, is people found faster ways of doing matrix multiplication than you would expect. And so if you think about two matrices, A, B, C, D, and in a Straka, E, F, G, H, and you look at how many multiplications, well, I multiply A times E plus B times G, A times F plus B times H, C times E plus D times G, C times F, D times H. That's 8 multiplications. Someone found a way to do it with 7. Now, they have to do more additions, but addition is cheaper than multiplication. And so you might think, OK. But it turns out this is one of the most useful things in 20th century mathematics because it means they can do these processes much faster. And as the matrix size gets larger and larger and larger, the savings actually propagates exponentially. So if people are interested, this is definitely something we could look at next time as to how do you compute something like this fast? One of the applications as to why we might care about something like this is related to cryptography. So RSA, which for years was one of the most common ways of encrypting, decrypting information, a lot of it comes down to being able to do multiplication very, very quickly. And so what we're doing, just to give a quick recap, is we're looking at a matrix formulation. And so if I let my vector Vn plus 1 be Fn plus 1 Fn, where they're the Fibonacci's, and the previous state is Fn, Fn minus 1, I can write the current state, now expand out using the recurrence relation, and then it turns out it's this matrix 1, 1, 1, 0 times the previous state. So I have this transition matrix, and every time I apply the transition matrix, I move one more. So my final state is actually just applying the transition matrix n times to the initial state. And so if I can just figure out high powers of this matrix, I can see how things go. It turns out we can use something very similar to understand the whales. And so what I'm doing here is I'm trying to understand how the whale population evolves in time. I'm just double checking to make sure it's recording. Yep. So we said whales die after 4 years. Nothing really happens when they're born. For their first year of life, they basically do nothing. Then when they turn 1, each pair of wheel generates 2 new pairs of wheels. When they're 2, they generate another pair of wheels. Then when they're 3, they enjoy their old age, dot on their kids and grandkids. And then when they're 4, they die. So we'll make it die at 4 years. OK, this is not necessarily the most reasonable model, but let's see where this gets us. So what I'm going to do is I want to try to figure out how to model this. And then once we model this, we'll see it's very similar to the Fibonacci case. And then we can make the model more reasonable at the cost of making the analysis more complex. So what we'll do is the following. So AN will be the number of whale pairs born in year n. Bn will be the number of whale pairs that are 1 year old at year n. Cn, Shaka, will be the number of whale pairs that are 2 years old at year n. Dn will be the number of whale pairs that are 3 years old at year n. Do I need an En? They're dead, exactly. And in the Star Trek analogy, they're dead, Jim. OK? Don't have to worry about anything further. OK? I want to understand how they change. So now I'll have my vector Vn will be An, Bn, Cn, Dn. And let's figure out how they change. So in year n plus 1, how many wheels are born? I'm sorry? So how would you write this? So it would be 2bn for all the wheels that were 1 year old the year before. And then, well, it would be 2, no, I think it's 2an. It's 2an. Right. It's 2an plus 1bn plus 0cn plus 0dn. I know there's a lot of zeros, but it'll just make it easier to see the matrix. Because if you're born in year n plus 1, how did that happen? Well, so let's, it's actually a little bit easier if we do it in reverse. How many wheels in year n plus 1 are 3 years old? It's just the number from the year before that were 2. So dn plus 1 would be 0an plus 0bn plus cn plus 0dn. The number of wheels in year n plus 1 that are 3 is just how many wheels were 2. No wheels ever die except from old age. How many wheels in year n plus 1 are 2 years old? Well, it's all the ones that were 1 year old the year before. So it would be 0an plus 1bn, put the 1 there, plus 0cn plus 0dn. Then how many wheels are 1 year old? It's the wheels that were just born the previous year. So it would be 1an plus 0bn plus 0cn plus 0dn. And now, how many wheels are born in year n plus 1? All the wheels that were born in year n, now 1 year later, they're 1 year old, and they each generate 2 pairs of wheels. And then anybody who was 1 year old in year n is now 2 years old in year n plus 1, and will generate 1 pair of wheels. So we get the following, an plus 1, bn plus 1, cn plus 1, dn plus 1 is just this bigger matrix now, 2, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. an, bn, cn, dn. And we can keep playing the same game. So if we call this matrix A, then we would get that this would be, an plus 1, and then just the initial populations, A0, B0, C0, D0. So this is now a system of difference equations. The Fibonacci's was just one difference equation. This is a system. And we can represent this as a matrix so we can quickly compute what's going on. You can also play games and create just one massive equation and solve it directly. I just want to try to give you some ideas of applications of stuff like this. This is often called a Leslie matrix. So it has names in biology. Oh, yeah, you were doing Leslie matrices? Oh, excellent. Oh, no. Now, if you look at this matrix, something looks really strange about this matrix. Yes, we've got this, all this nice ones here, which is basically just telling us we have this really nice shift. How important is dn and what goes on? Really, dn doesn't have that much of a role because you have all zeros here. So this allows you to talk about some things in biology. There are a lot of, I think the technical term is critters, that lay their eggs and then leave. And then from an evolutionary biological standpoint, if all they do is leave and they never interact, then for the point of view of the survival of the species, it doesn't matter what happens to them. If they have more children, then that's different. But if they only do it once, then it doesn't really matter what happens to them because they're no longer involved. So here, the question is, these whales that are old, are they doing anything to keep the rest of the herd safe? Now, it's really bad not to have any whales dying from natural causes or predators. So what you might want to do is, maybe you don't always make it to the next year. We could replace these ones with probabilities. And so what we could do is we could have random matrices. And now when it becomes random matrices, it becomes very hard to say what's going to happen exactly, but you can do simulations and you can do some theory. You can say, with 95% confidence, we believe the populations will be in this range in the future. And so what you could say is, maybe I have a 95% survival rate. Maybe it's normally distributed with a standard deviation of 0.01. It can't be completely normally distributed because I'm not going to have whales all of a sudden emerge. I'm not going to have negative probabilities, but something like that. So you could have these numbers no longer be all ones. Same thing for the number of whales that are born. They don't have to always be just 2 and 1. You can allow these to vary as well. And now it all comes down to, how do you compute high powers of this matrix A? Or more generally, if you have a sequence of random matrices, what can you say about a product of a sequence of random matrices? And so what I like about this is you start off with a completely unrealistic model, but it's easy to analyze. And then you see, as you try to have the model do a better job describing reality, you see the real challenges in being able to say anything meaningful. But in the deterministic setting, it turns out we can calculate high powers of this matrix very quickly, and we can jump to what the real population would be. In principle, it's not hard to figure out what the real population is. Just keep applying the matrix A. But if you want to see what's going to happen after 1 billion years, well, you'd like to be able to jump. But I want to just give you some sense of why you might care about recurrence relations. And then I have, I think, just enough time before the pizza arrives to give the worst application of the Fibonacci numbers known to man, woman, or child. It is the worst. It is the most absurd. It is the most ridiculous application of the Fibonaccis. I wish I could take credit for being the one to discover this. It's not entirely clear who was the first one to make this observation. I have heard strong claims of a certain person whom I know and admire. I wouldn't be surprised if this was their handiwork. So I told you earlier that there's a lot of different definitions of the Fibonaccis. So I want to do Zeckendorf's theorem. And then this is one of my favorite theorems to talk to students about. So I'm going to define the Fibonaccis a little bit differently. I'm going to keep fn plus 1 equals fn plus fn minus 1, because if I change the recurrence, there's no way you'll allow me to call it the Fibonaccis. But now I'm going to start f1 equals 1, f2 equals 2. So I'm eliminating the 0, and I'm eliminating that extra 1. And there's a reason I'm doing this. So now my sequence is 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, yada, yada, yada. So here's the theorem. Every integer, well, let's do positive integer. Every positive integer has a unique representation as a sum of non-adjacent Fibonacci numbers. That's Zeckendorf's theorem. So I'm responsible for, in some sense, the worst proof known of this, but the proof I have generalizes to other problems much better than other approaches. And so in the end, it was a good theorem. I'm going to show you the computer science proof. The computer science proof is through the greedy algorithm, which we've seen before. I'll only do half the proof. So give me a number. 7? Can we make it a little bit larger? Can we make it 77? 72. So so this is proof by example. All right, so let's take 72. Let's subtract the largest Fibonacci number we can from it. So what's the largest Fibonacci number we can subtract? So we subtract 55, and what's left over? 17. And then we subtract the largest Fibonacci number we can from 17, which is 13. And now we're left with 4. We subtract the largest Fibonacci number we could, which is 3. And then we're left with 1. And subtract the largest Fibonacci number. If at any point we subtracted 2 Fibonacci numbers that were adjacent, then that contradicts that at the previous step we subtracted the largest one we could. Imagine that when we were doing it, we subtracted 55 and 34. Well, if we subtracted 55 and 34, why didn't we subtract 89? So because we're always throwing away the largest one we can, when we look at what's left over, if we could throw away the one that was right next to that, then we did a mistake earlier. We didn't throw away the largest one we could. So in some sense, you now prove this by induction. We can write 1 as the sum of non-adjacent Fibonacci numbers. Not too bad. We can write 2 as the sum of non-adjacent Fibonacci numbers. Not too bad. We can write 3 as the sum of non-adjacent Fibonacci numbers. Not too bad. We can write 4, 3 plus 1. Now we could proceed by induction. Assume your number is larger than 4. Subtract the largest Fibonacci number you can. And now you're left with something smaller, which by induction has a decomposition. So you now just continue by induction, and you prove that a decomposition exists. So go by induction. Did the base case? Has everybody seen proof by induction? Okay, so we do the base case and then the inductive step. So all that's left is we have to show uniqueness. So for uniqueness, imagine we had 2 different decompositions. So we have some number x, and we can write it maybe as f k1 plus f k2 plus f km. And let's assume we can also write it as f L1 plus f L2 plus plus f Ln. We don't know they necessarily have the same number of summons. So we have to show x can't have 2 different decompositions. And so there are 2 cases. The largest numbers are the same, or the large numbers are different. So case 1, fkm equals fln. Well, if these large numbers are the same, we can remove them, and then by induction we have a smaller number. And we've shown by induction that everything up until x minus 1 has a unique decomposition as a sum of non-adjacents. So because these are the same, we can remove it, and now we have a smaller number. So remove done by induction. So we now have a smaller number. If they were different, so case 2, let's assume fkm is greater than fln. So we have to show that this can't happen, that they have to have the same first number. Well, let's assume that we have this. The largest it could be, let's say ln equals 12. The largest it could be is f12 plus f10 plus f8 plus f6 plus f4 plus f2. Do you agree that that's the largest it could be if it starts with ln equals 12? Because I've got a sum of non-adjacent Fibonacci's, so the best possible is to have all of them. And we'll assume that km is greater than or equal to 13. Because they're not equal, so let's assume this one is largest. If I add f1, I make this larger. So now let's add f1. What's f1 plus f2? F3. F3 plus f4. F5 plus F6, F8 plus F7, F9 plus F10, F12 plus F11, F13. So we now get, if this is x, then x plus 1 is equal to F13. And because this one has at least an F13, it's got to be larger. So this proves uniqueness. So every Fibonacci number has a decomposition, and if you have two different decompositions, they have to be different numbers. And the easiest way to see this is look at the worst possible case. I love looking at worst possible cases. You know, the worst possible case is I have every single term, and if I then add 1, I get up to F13. So another way of saying this is the sum of my numbers, all these Fibonacci numbers, it can't be larger than one more than this. So there's no way that they would be equal. So every number has a decomposition, and every decomposition is unique. Okay? All right. Is everybody ready for the worst application ever of Fibonacci's? Okay. So let's take 72. So we know 72 is equal to 55 plus 13 plus 3 plus 1. Okay? So this was the first Fibonacci, second, third, fourth, fifth, sixth, seventh, eighth, ninth. Okay? So we're saying that 72 equals F9, 13 is F6, F3 is 3, good, plus F1. Okay? I'm going to shift all the indices up by 1. Okay? So this is going to be 2. F4 is 5, I think. F7 is 21. And F10 is 89. Right? Oh, no, wait. F10 is 89. OK. So now we have to do a little bit of arithmetic. So 89 plus 21 is 90, 110, 117. Does anybody know the approximate relation between 72 and 117? I'm sorry? So we were talking about driving earlier today. Is 72 miles per hour a reasonable speed? On the Mass Pike. I mean, I, of course, will not go 72 because the posted speed limit is 65. And I believe in obeying all posted speed limits. But other people who don't care as much about the rules and laws of the Commonwealth of Massachusetts, would you be surprised to see a car going 72? No. Actually, I might be surprised if the car was only going 72, but 72 is not an unreasonable rate. But imagine, you know, I'm in Williamstown. I actually have Canadian money on me because I'm not that far from the Canadian border. I go to Canada fairly frequently. What do they do in Canada that we don't do for speeds? So how many kilometers per hour is 72 miles? 170. Approximately. So what's the conversion factor? 1.6. So can somebody multiply 72 by 1.6? Or what the actual value is? So it's equal to 115.2. So it's kph, sorry. So why does shifting the indices in the Zeckendorf decomposition approximately give you your speed in kilometers per hour?
Gotta give you some number.
So what's the conversion factor? 1 mile per hour equals about 1.62, you said, kilometers per hour? What's the
6.2 miles? Yeah.
1.613 kilometers per hour. Can you calculate 1 plus the square root of 5 over 2, the golden mean? 1.618. Now, we had Binet's formula. The nth Fibonacci number, how does that compare to the n minus first? Well, Fn was approximately 1 over root 5, and I'm going to use phi for the golden mean to the n. So phi is 1 plus root 5 over 2. The nth Fibonacci number is approximately this. The n plus first Fibonacci number, then, would be approximately 1 over root 5, golden mean to the n plus 1. So the ratio of Fn plus 1 to Fn is approximately the golden mean. So when your numbers are large, if you move your index up by 1, you are approximately multiplying by the golden mean. This is where you get... And so when you look at this, because the golden mean is almost the same as the conversion factor between miles per hour and kilometers per hour, if you shift all of these by 1, you are approximately multiplying each one of them by the golden mean, which is approximately the conversion factor. And what's nice is the numbers that really matter are the larger ones. The smaller ones have much less of an impact on your speed. And so if you need to figure out what your speed could be near the Canadian border, this is one of the longest ways possible to do the calculation. It's a lot of work. But you don't have to multiply by 1.6 anymore. You just have to shift, exactly. And so the question is always, how do you do operations? To multiply by 1.6, I might double, and then double again, and double again, double again. So if I double 4 times, that's 16, and then divide by 10. How do you do math? How do you do the operations? So this is a fun coincidence. There's really no good applications of this. But what I like about this is beginning to get into research I do with my students. So a nice question would be, how many summons does a typical Fibonacci number have? How many summons does a typical number have when you decompose it? So let's say you look at everything between the 200 and the 201st Fibonacci number. It turns out that the number of summons is approximately 200 divided by something related to the golden mean. If you look between the... So this number here, 72, has 1, 2, 3, 4, has 4 summons in its decomposition. So it turns out that the number of summons is normally distributed in the limit. So if you look at how many numbers have exactly 1 summon, 2 summon, 3 summons, it becomes normally distributed, and the mean grows as you go further down. You can ask, what's the gap between summons? How often do you have a gap of 1? Well, never, because they can't be adjacent. How often do you have a gap of 2, 3, 4? It turns out it's geometric decay. You can ask, what's the longest gap between summons? And it turns out we have answers for stuff like this. A lot of this is very similar to tossing a coin. So if you want to think about tossing a coin, you can represent it as either a 0 if it's a tail or 1 if it's a head. Think of it as writing a number in binary. And so when you toss a coin, you're recording the number by recording its digits in binary. And you can ask, how many numbers do you expect to use? Well, if I toss the coin n times, about how many heads do you have? About n over 2. And the fluctuations about that should be Gaussian. And then you can ask, how many alterations do I expect to have between tails and heads? What's the longest run of heads do I expect to get when I toss a coin? So when you teach probability, students know, if you toss a coin 100 times, you get about 50 heads, about 50 tails. People are very bad at some of the more involved tests as to, is the sequence really randomly generated, or did the students just make something up to look random? So how many of you have heard of IRS gate? This is where a couple of people in the Internal Revenue Service were denying 501c requests from certain organizations that were conservative or had conservative sounding names. Some of them changed the names to progressive or liberal and were immediately approved. They were being denied for political reasons. The former commissioner of the Internal Revenue Service at the time was named Stephen Miller. I sometimes show both of our pictures together. He ended up losing his job because of this. And so there are good ways to tell when fraud is happening. And so people are often very interested, is something happening fraudulently or not? So the IRS is very interested, are you making up your corporate data? Are these your actual numbers? How can we test and see if this is reasonable? Every string, if heads and tails are equally likely, every string is as likely as every other. So in some sense, well, every string is equally likely, so why are you getting on my case for this? Well, while they may all be equally likely, there are certain patterns that you would expect to see. You would be shocked if the number of heads and tails aren't approximately the same. Most people know enough to, if they're creating a fake sequence of data, to do something like that. But people don't know more refined things. They don't know what should be the longest run of consecutive heads. Did we do roulette before? Excellent. So we will then, after pizza, we will go into roulette. And we will show how the Fibonacci numbers can be used to deal and understand roulette. And it's one of my favorite applications of the Fibonacci numbers. Now, it's not going to be exactly the Fibonacci's. It's going to be a close cousin of the Fibonacci's. But this is going to explain to you why you should not go to Vegas and play the following strategy. A lot of people think, there's nothing wrong with this. I'm going to make millions. No, there is an error, and I will show you what the error is. But people want to detect, has something been altered? Is this the real data? And because the IRS, for good or for ill, only has finite resources, they want to figure out what's the more likely fraudulent case. What's the more likely company that's cheating? That's the one we want to investigate. So it's a good way to allocate resources. And so one of the questions is, how many runs of heads do you expect? How many alterations between heads and tails? What's the longest run of heads do you expect? You can ask all these questions for here. These are terrific questions to ask. You can have students numerically investigate this. And then once you get the data, you can start to make conjectures as to, if you were to flip a fair coin 100 times, would you be surprised if you saw 5 consecutive heads? Would you be surprised if you saw 10 consecutive heads? Where does it get surprising? How much out of line? So one of my favorite examples, and this leads into Benford's law, is if you look at data sets, not all digits are equally likely to start a data set. So it turns out in a lot of data sets, you're more likely to start off with a 1 about 30% of the time than you are with a 9 only about 4.6% of the time. So when people are making up numbers, they often make numbers up the wrong way. And so certain tests will, we see too many of these numbers. And one of my favorite flags is if you lose a credit card, what do you do? Cancel it. Are you liable for the charges? No, which is wonderful. So what happened is there was a credit card company where they did an internal investigation, they looked at the numbers, and they noticed a few more numbers were starting with a first digit of 4 than they would expect. So they looked a little bit further, and they saw a lot of them, their first 2 digits were 4849. They looked a little further, they were about 4800, 4900. And a lot of them were due to one person. What this person was doing was they were having their friends get credit cards from the bank and run up debts of just below $5,000 and then call, you lost your credit card? Oh, I'm so sorry to hear you lost your credit card. Don't worry, we're canceling the credit card. You're not liable for any of the charges. He had the ability to just write off and pay anything $5,000 or less without an internal investigation. The reason is, imagine you're a big, multi-billion-dollar credit card company. If somebody tells you, we've lost a credit card, there's $27.15 in disputed charges. Do you want me to hire an investigator to track down? No. Just eat it. What if it was $28,000? All right, let's send somebody to investigate. So what they did, which was stupid, is they had a hard cutoff that people knew. Anything below 5,000 would not be investigated. What you need to do is you need to randomly investigate some of them. If you think about screenings in the airports, this is why the elderly grandmother in the walker, every now and then you need to send such a person for additional testing, because otherwise you now know, here's a protected category that will not be investigated. This doesn't mean that you should be investigating grandmothers like that with the same frequency as other people, and I'm not going to say anything else before getting into trouble. But in terms of allocating finite resources, if you have a certain area that's never investigated, then people can take advantage of that. And so they found that this one person was just excusing debts of their friends and doing it mostly under the radar gun. And then when they did this digit analysis, they discovered it. So a lot of the questions like this can lead into what's called data integrity tests. So just because something's been reported to you doesn't mean that the numbers are accurate. Sometimes there is a transmission error. How can you tell if something has been misrecorded? So decompositions like this and asking questions like this, they actually lead to some really good tests. So I've been trying to stall for a minute or two because you said the pizza would be here by 12:10 at the latest.
Lori went to, I think, to get it.
Right.
We can rest.
All right, so I would say let's stop right here. And then we'll see roulette afterwards. So I can't stop